Hello dear students, let us solve some numerical problems related to elasticity. At first, let us review the related formulas. Stress is defined as the force per unit area. Next, longitudinal strain is the ratio of change in length upon and original length. Volume strain is the ratio of change in volume upon original volume. Young's modulus of elasticity y is equal to stress upon longitudinal strain. Stress is force per unit area. Longitudinal strain is change in length upon original length, which may be written as f into length, initial length upon a into change in length. Bulk modulus of elasticity is denoted by capital K or B, which is stress per unit volume strain. Modulus of rigidity or shear modulus of elasticity denoted by eta and is the ratio of tangential stress to the shearing strain, where shearing strain is angle of shear in radians. Energy stored in stretched wire is equal to half into force into change in length. Energy density, which is energy stored per unit volume, is equal to half stress into strain. Thermal force or tension is given by F is equal to Y A alpha delta theta, where a rod of cross section area A is fixed between two fixed rigid supports like this, and its temperature is changed through angle delta theta. Then the force of tension experienced by the rod is given by this relation, where alpha is linear expansivity of rod material, delta theta is temperature change, A is cross section area of rod, and Y is Young's modulus of elasticity of material of rod. Now first question, a steel wire of length 2 meter, cross section area 4 millimeter square and Young's modulus 2 into 10 to power 11 Newton per meter square is stretched through 2 millimeter. Find elastic energy stored in the wire. Now solution to question first. Given L 2 meter, A 4 mm square, which is 4 into 10 to minus 6 meter square. Young's modulus 2 into 10 to power 11 Newton per meter square. We have to find elastic energy stored. Elastic energy stored. Elastic energy stored is 1 by 2 F into delta L, because Y is equal to F L upon A into delta L. Therefore, F will be equal to Y A delta L upon L. So this can be written as 1 by 2 Y A delta L upon L into this delta L. Here delta L is also given to be 2 millimeter, which is 0.002 meter. Now this is 1 by 2 Y A into delta L square upon L, which gives 1 by 2 into 10 to power 11 into 4 into 10 to minus 6 into 0.002 square upon L. L is original length 2, which on simplification gives 0.8 joules. Now second question, what force must be applied to a steel wire of length 6 meter, diameter 1.6 millimeter and Young's modulus 2 into 10 to the power 11 Newton per meter square to produce an extension of 1 millimeter? Solution to question 2. Here given length is 6 meter, diameter 1.6 millimeter, therefore radius will be equal to 0.8 mm, which is 0.8 into 10 to minus 3 meter. Young's modulus 2 into 10 to the power 11 Newton per meter square. Force is to be calculated. Extension is 1 millimeter, means 0.001 meter. Now y is equal to FL upon A delta L. Therefore F will be equal to y A delta L divided by L. F will be equal to y is 2 into 10 to the power 11. A is pi r square. Pi r is 0.8 into 10 to minus 3 square, pi r square, into delta L is 0.001 upon, this is y A delta L upon L. L is 6, which gives required force as 67.2 Newton. Next question number 3. Uniform steel wire of density 8000 kg per meter cube, length 2.5 meter and mass 20 gram lengthens by 1 millimeter due to 80 Newton force. Find Young's modulus and energy stored. Now, question. Solution to question 3. Given density 8000 kg per meter cube, length 2.5 meter, mass, this is mass of wire, 20 gram, which will be equal to 20 upon 1000 means 0.20 kilogram. Applied force is 80 Newton. We have to find Young's modulus and energy stored. First, Young's modulus y is equal to F L upon A delta L. Because density is equal to mass upon volume. This is mass upon volume is length into cross section. It gives A as m upon L into rho. Therefore, y will be equal to F L upon A means m upon rho into L into delta L, which can be written as F rho, this L goes here, L square upon delta L, get y as 2 into 10 to the power 11 Newton per meter square. Second part is energy stored. Is half F into delta L, which will be 1 by 2, F is 80 and delta L is 0.001. So we get energy stored as 0.04 joules. Now question number 4. What stress would increase the length of a wire by 1/10 of 1% of initial length? Also find force if Young's modulus is 2 into 10 to the power 11 Newton per meter square and radius is 0.28 millimeter. Question number 4. Solution to question number 4. Given radius of wire 0.28 millimeter means 10 to minus 3 into 10 to minus 3 meter. Young's modulus 2 into 10 to the power 11 Newton per meter square. Delta L is 1/10 means 1 upon 10 into 1% means 1 upon 100 of initial length, which is 1 upon 1000 means 0.001 times L. We have to find stress first. Stress will be equal to y into strain, because y is equal to stress upon strain. Therefore, stress will be y times strain. Y into strain is 0, change in length upon original length. This is 2 into 10 to the power 11 into 0.001 L upon L. L cancels and we get 2 into 10 to the power 8 Newton per meter square. Second part, force stress is equal to force upon area, force upon pi r square. Therefore, F will be equal to pi r square into stress. Pi r is 0.28 into 10 to minus 3 square into stress is 2 into 10 to the power 8, which gives 49.26 Newton. Next question number 5. A steel wire and a copper wire, each of length 1.5 meter and radius 1 millimeter, are joined at one end. The composite wire is loaded until final length becomes 3.003 meter. Find the applied force and strain in each wire. Young's modulus of steel and copper are given. So, solution to question 5 given. Total final length minus total initial length. R is 1 millimeter, radius of each wire 0.001 meter, length is 1.5 meter. This is length of steel and length of copper. This is radius of steel and radius of copper. We have to find the force applied and strain in each wire. Now, Y steel will be equal to F, because F and A are same, F into A, so Y steel will be equal to F into L upon A into delta L of steel. Therefore, delta L of steel will be equal to F into L upon A into YS. Here, initial length of each wire, applied force and cross section area are same for both cases. Similarly, delta L of copper will be equal to F L upon A into Y of copper, but total change in length is equal to sum of these two. So delta L of steel plus delta L of copper, this is 0.003. FL upon A are constant, FL upon A are common in both, FL upon A are common in both. This is 1 upon Y steel plus 1 upon Y copper. This gives applied force F as 0.003 into A upon L into 1 upon YS plus 1 upon Y C. Where this is 0.003, A is pi into 0.001 square upon L is 1.5, length of each wire, and to 1 upon 2 into 10 to power 11 plus 1 upon 1.2 into 10 to power 11, 471.2 Newton. 471.2 Newton. Second part, strain. Strain in steel will be equal to stress upon Y steel, because Y is stress upon strain, therefore strain will be equal to stress upon Y. Stress is force upon area into ys. Force has been calculated to be 471.2 upon 8 pi r 0.001 square into ys is 2 into 10 power 11, which gives strain in steel as 7.5 10 to minus 4. Similarly, strain in copper wire will be equal to F upon A into Y copper 471.2 upon pi 0.001 square into 1.2 into 10 to power 11, which gives strain in copper wire is 1.25 into 10 to minus 4. Given this is a brass cylinder of length 0.5 meter, radius 0.01 meter, Young's modulus 3.5 into 10 to power 10 Newton per meter square. It is loaded with mass 5 kg. Then we have to find contraction, means decrease in length. Second, we have to find the energy stored. Now, first part, y is equal to F L upon A delta L, where therefore delta L will be equal to F L upon YA. F is mg into L upon y into pi r square, which gives m is 5, g is 9.8, L is 0.5 upon y is 3.5 into 10 to power 10 into pi r square. Pi r 0.01 square, which gives delta L as 2.23 into 10 to minus 6 meter. F is mg 1 by 2 m into g into delta L 1 by 2, m is 5, g is 9.8, delta L is 2.23 into 10 to minus 6, which gives 5.5 into 10 to minus 5 joules. Next question number 7. Question is, rubber cord of a catapult of length 10 cm and cross section area 1 millimeter is pulled to 12 cm and a missile of mass 5 gram is projected with it. Find the initial velocity of projection. Young's modulus is given. Here catapult means gulel. Solution given for rubber cord of catapult. Catapult means gulel. cross section area is 1 millimeter square, which is 1 into 10 to minus 3 meter square, means 10 to minus 6 meter square. Initial length is 10 cm, means 0.1 meter. Final length is 12 cm, therefore change in length will be 12 minus 10 cm, that is 0.02 meter. Mass of projected missile, which may be stone, is 5 gram, which is 0.005 kilogram. Young's modulus is 5 into 10 to power 8 Newton per meter square for rubber. We have to find velocity of projection. Now, from energy conservation law, in this case, energy stored of F into delta L must be equal to the kinetic energy gained half mv square. Half cancels out, and we get V as F delta L upon m under root because y is equal to F L upon A delta L. Therefore, F will be equal to y A delta L upon L. So, V will be equal to F is y A delta L upon L. This is F. This is delta L upon m. Now values are known. We get D is equal to y is 5 into 10 to power 8. A is 10 to minus 6 upon L is 0.1, M is 0.005, and delta L into delta L becomes delta L square, which is 0.02 square, which gives velocity as 20 meter per second. Next question number 8. Calculate the minimum tension needed to keep a platinum wire of diameter 1 millimeter. Young's modulus 17 into 10 to power 10 Newton per meter square, and linear expansivity 9 into 10 to minus 6 per Kelvin. Tau between two fixed invar frames, and temperature rises by 100 Kelvin. Solution to question 8. Given temperature change delta theta is equal to 100 Kelvin or 100 degree Celsius. Young's modulus 17 into 10 to power 10 Newton per meter square for platinum. Linear expansivity alpha 9 into 10 to minus 6 per Kelvin. Diameter is 1 millimeter, therefore diameter is 1 mm, which may be written as 1 into 10 to minus 3 meter. We have to find force when the wire is fixed between two rigid supports. Now, thermal force F is equal to y a alpha delta theta, y a means pi d square by 4 or pi r square into alpha delta theta, values are known, y 17 into 10 to power 10 into pi d is diameter is 1 into 10 to minus 3 square pi d square by 4 into alpha is 9 into 10 to power 9 into 10 to minus 6 into 100, which on simplification gives force as 1.2 Newton. Next, question number 9. Find the force needed to punch a hole of diameter 1 cm in a steel sheet of thickness 5 mm if the shearing strength is 2.76 into 10 to power 8 Newton per meter square. Solution to question 9 given. We have to find the force needed to make a hole of diameter. D is equal to diameter of hole 1 cm, 0.01 meter. Therefore, radius will be equal to d by 2, 0.01 upon 2 is 0.005 meter. Thickness of sheet, suppose denoted by T, is 5 millimeter, 0.005 meter. Shearing strength, .76 into 10 to power 8 Newton per meter square. Now, shearing strength will be equal to force per unit area, simply stress. Area is, this is force per unit area is 2 pi r into thickness, area of hole. This gives F as 2 pi r into thickness into shearing strength 2 pi r is 0.005 into thickness is 0.005, 2 pi r into T into shearing strength is 2.76 into 10 to power 8. On simplification, we get the force as 4.34 into 10 to minus 3 Newton. Next, question number 10. Rubber cube of each side 8 cm has one side clamped and tangential force of 256 kg weight is applied to opposite face. Find shearing stress and shearing strain if modulus of rigidity is 1.86 into 10 to power 7 dyne per cm square. Solution to question 10 given. Modulus of rigidity (1.87 into 10 to power 1.86 into 10 to power 7 dyne per cm square. Area will be equal to 8 cm into 8 cm square, 64 cm square. Force is equal to 256 kilogram weight, which will be equal to force is 256 kilogram weight, which is 256 into 9.8 Newton, and 1 Newton is into 10 is equal to 10 to power 5 dyne. Therefore, it will be 256 into 9.8 into 10 to power 5 dyne. We have to find the shearing stress and shearing strength first. Shearing stress will be force per unit area. Force is 256 into 9.8 into 10 to power 5 and area is 64. So, shearing stress in CGS system is 3.92 into 10 to power 6 dyne per cm square. First part. Second, eta is equal to shearing stress upon shearing strength Therefore, shearing strength will be equal to shearing stress divided by eta. Shearing stress 3.92 into 10 to power 6 upon eta is 1.86 10 to power 7. We get shearing strain. Therefore, we get shearing strain as 0.2 radian. Next question number 11. A spherical ball contracts in volume by 0.01% when subjected to a pressure of 100 atmospheres. Calculate bulk modulus in CGS units. Solution to question 11. Here given delta V is equal to 0.01% means upon 100 of V. Pressure which works as stress 100 atmospheres, that is 100 into 1.01 into 10 to power 6 dyne per cm square. So we have to find the bulk modulus. Therefore, K will be equal to stress upon volume strain stress is, this is 1.01 into 10 to power 8, 1.01 into 10 to power 8. Strain is, volume strain is delta V upon V 0.0001 from here 0.0001. So bulk modulus will be equal to 1.01. This will be 1.01 into 10 to power 12 dyne per cm square. Next question number 12. A railway track uses long welded steel rails which are prevented from expanding by clamps. Find energy stored per kilometer if Young's modulus is 2 into 10 to power 11 Newton per meter square, cross section is 75 cm square, change in temperature is 10 degrees Celsius, and linear expansivity alpha is 1.2 into 10 to power minus 5 per Kelvin. So, solution to question 12. Thermal stress are given. Length is 1 kilometer means 1000 meter. Area is 75 cm square, which is 75 into 10 to minus 4 meter square. Linear expansivity alpha 1.2 10 to minus 5 per Kelvin. Young's modulus 2 into 10 to power 11 Newton per meter square. Now, thermal force or thermal tension F is equal to Y A alpha delta theta. Y is 2 into 10 to power 11. A 75 into 10 to minus 4. Alpha 1.2 into 10 to minus 5. Delta theta 10, which gives force as 1.8 into 10 to power 5 Newton. Now, energy stored will be equal to 1 by 2 F into delta L, because Y is equal to F L upon A delta L. Therefore, delta L will be equal to F L upon Y A. So, this will be 1 by 2 F into delta L can be replaced with F L upon Y into A, which will be 1 by 2 L F square upon Y A. Values are known. 1 by 2. L is 1000. F is 1.8 into 10 to power 5. It's a square. Y is 2 into 10 to power 11. And A is 75 into 10 to minus 4. Energy stored per kilometer as 10,800. Millimeter. When a force of 1.5 Newton is applied on it, calculate the energy stored in the spring when hanging vertically supporting a mass of 0.2 kg. If the spring were unstretched before suspending mass, calculate the potential energy of mass when why these two energies are different. Solution: because Young's modulus Y, cross section area A, and initial length are constant for both cases. Therefore Y will be equal to F1A. Therefore Y will be equal to F1 L A upon delta L1, which is F2 L upon A delta L2. This gives delta L2 as F2 delta L1 upon F1. Values are known. 2 into 0.03 upon 1.5. That is delta L2 will be equal to 0.04 meter. Therefore energy stored will be equal to 1 by 2 F2 into delta L2, 1 by 2 into 2 into 0.04, that is 0.04 joule. First part. Now second part. Loss of potential energy of mass will be equal to mg into h, where h is equal to delta L2. So it will be m 0.2 g 10 delta L2 is 0.04. This will be equal to 0.08 joules. Energy stored and loss of potential energy are different. The energy equal to the difference between potential energy loss and energy stored is converted into heat.